And if you're ready, let's get started.
Yeah, can you hear me?
Yes.
Okay. Hello everyone. Today I'll be presenting a paper titled DIOR, Adaptive Cognitive Detection and Contextual Retrieval Optimization for Dynamic Retrieval-Augmented Generation. This paper is published in ACL 2025, and I am Minjeong from KAIST. Let's start with a brief introduction to Dynamic Retrieval-Augmented Generation. I think everyone knows about RAG, which has emerged as an innovative approach to mitigate hallucinations by integrating external knowledge bases. While conventional RAG methods typically involve a single-turn retrieval process based on the initial query, this method often falls short when dealing with complex texts, such as multi-step reasoning, long-form question answering, or COT reasoning. This is where dynamic RAG comes in. It addresses these shortcomings by employing multi-turn retrieval during the generation process. Dynamic RAG generally involves two main steps. First, selecting the appropriate retrieval timing, and second, constructing an effective query once retrieval is triggered. Existing dynamic RAG methods such as fixed length RAG and fixed sentence RAG methods, they just simply trigger the retriever after every n token or each sentence, and then use each generated tokens or sentence as a new query. However, these methods often fail to fully consider the real-time needs during the LLM generation process. For more recent methods, they try to trigger retrieval when uncertain tokens are encountered, and they determine the timing and contents of retrieval based on the LLM's attention, entropy, and token relevance. However, existing dynamic RAG methods face significant limitations, which serve as the primary motivation for the DIOR paper. The first key limitation is the lack of effective mechanism to control retrieval triggers. Current dynamic RAG strategies often rely on static, predefined rules, such as triggering retrieval when the generation probability of a token falls below a certain threshold. However, a low generation probability merely indicates low confidence in a token. It doesn't necessarily mean a hallucination will occur after the LLM generates the task. Furthermore, more existing methods trigger retrieval after hallucinations occur. They fail to predict whether the LLM has the capability to answer a question before the generation, which could prevent hallucinations proactively. This led to ineffective timing for retrieval triggers. And the second major limitation is the lack of effective scrutiny of retrieval content. Existing methods often perform single batch retrieval in each round and rely on confidence scores of recently generated sentence to determine retrieval keyword for a query. This approach often fails to capture semantic relationship within the overall contextual requirements of the task. As a result, it can lead to the retrieval of irrelevant documents, which increases computational cost and leads to repeated retrieval triggers. And additionally, retrieving excessively long documents can hinder the LLM's understanding due to information overload. Let's move on to the method. So the DIOR addresses these limitations through two main components. The first one is adaptive cognitive detection. This component is responsible for deciding when to trigger the retriever. And they train two classifiers for this component. First one is early detection, which assesses the model's ability to answer question before the generation. And second one is real-time detection, which monitors for hallucination during the generation process. And the second component is contextual retrieval optimization. These components focus on what to retrieve and how to effectively process and utilize the retrieved documents after the retriever is triggered. For this component, they optimize the priority of query keywords through context analysis. And they did stepwise retrieval, where the retrieved documents are used to capture new concepts to refine query keywords. And finally, they use sentence-level chunking module to reduce the impacts of long text. Before delving into details, I'll briefly explain the mechanism of DIOR. So when the query comes in for input, the early detection assesses the LLM confidence, whether the LLM can answer with this query without any external knowledge. And if LLM is not confident, then the retriever is triggered. And in the case, they extract keywords from the original query and do stepwise retrieval in here. They retrieve the documents with these keywords and use retrieved documents to new keywords for next step. And they retrieve with these new keywords and get the new documents. And then finally, they get documents and utilize this chunk to generate the final answer. And let's back to the early detection. If LLM is confident, then LLM just generate the answer without any external knowledge. And during the generation process, the real-time detection assess the hallucination of each token. And if the hallucination token is detected, the generation process directly stops and the retriever is triggered. In this case, they use the original query and generated text before the hallucination token to extract the keywords. And using with these keywords, they retrieve the documents and also they do the stepwise retrieval step in here. And finally, they use these chunks to answer the final answer. Yeah, and this is the mechanism of DIOR. And now let's delve into the details. As I mentioned before, the adaptive cognitive dictation is aimed to effectively judge the optimal timing of retrieval. And this consists of two classifiers, early detection and real-time detection. The early detection classifier is designed to assess whether the LLM can answer a question without external knowledge before generation. For data preparation, it uses a hallucination detection dataset, which its domain is Wikipedia, with tuple question, generated answer, GT answer, IG, and label. The IG stands for integrated gradients, which assess the model's focus on certain words within the question. I will explain more details about this IG on next slide. And the label 1 indicates hallucination if the generated answer is incorrect compared to ground truth answer. So for model training, they train on RNN classifier due to the sequential nature of the data. So they feed question, generated answer, GT answer, and IG into the RNN. and they predict the final hallucination level. A key aspect early detection is use of integrated gradients to generate feature attributions. This integrated gradients indicates the importance of each feature in a specific prediction. To effectively determine whether the LLM has enough information to answer a question without the external knowledge, they assess the model's focus on certain words within the question. So, whether the LLM can capture the key points of the question. So if the model's attention is dispersed, where the uniform distribution of attribution values, the entropy will be high, suggesting like uncertainty and a higher likelihood of hallucination. Conversely, if the model's attention is mainly focused on a few features, while the attribution values of other features are small or close to zero, the entropy value will be small because the model's attention is not scattered. And this reduces the uncertainty of the system. The second classifier is real-time detection, which monitors for hallucinations during the generation process. Unlike static rules that rely on token generation probability, this detector focuses on the accuracy of LLM-generated tasks. The detection process primarily focuses on change in entities, which are a common source of hallucinations. So the data is constructed by truncating Wikipedia articles after entities using LLM to continue generating tasks. And then entities are extracted from both original and generated tasks, and their semantic similarity is compared. If entities are not semantically similar, the generated task is labeled as a hallucination. And in this component, they train MLP classifier. And also they fit multiple set of data set to MLP classifier and predict the final hallucination level. So when is retrieval triggered based on these detectors? For early detection, I don't know why they define C of Q as the LLM confidence in question, because in here they label the hallucination case as 1. Then when the label comes to 1, it means that LLM generate the hallucinations. So anyway, if C of Q is 1, it means the LLM generated hallucination, so the retriever is triggered. In this case, candidate keyword for retriever is selected based on high IG attribution values, focusing on words the model should pay attention to. And for real-time detection, if hallucination probability of a generating token falls below to 0.5, the token is flagged as a hallucination and retriever is triggered. In this case, the candidate keywords are extracted entities from generated tasks, excluding those labels as hallucinations. And the second component is contextual retrieval optimization. As I mentioned before, this component is triggered when once early detections find LLM has no confidence or real-time detection identifies some hallucinations for token. It consists of three parts. For query formulation, they optimize the priority of query keywords through contextual analysis, and they do stepwise retrieval, where retrieved documents are added to query keywords for next retrieval step. And finally, for context utilization, they propose sentence-level segmentation approach, where they use sentence-level chunking module to reduce the impact of long context. So in pre-retrieval step, focus on optimizing the selection of query keywords. Instead of relying solely on recent token confidence, DIOR analyzed the entire generated text from detectors and identify a set of candidate keywords. And the importance of each candidate keywords is assessed using a weight sum of 4 evaluation metrics. The first one is attention score. It is from a multi-head attention mechanism indicating which parts of the text are most important for retrieval. By this attention score, the model can focus on various semantic and synthetic features of task. The second one is TF-IDF score to evaluate the information density of each token, and they prioritize those tokens with greater density. The third one is positioner score, which is based on the token's related position, considering its contextual role. It imposes high score to recent tokens. And the last one is semantic relevance, which is the cosine similarity between the token's word embedding and the query term. And finally, then DIOR ranks token by their importance score and prioritizing the most relevant ones. And then they retrieve documents based on these top ranked keywords. And these retrieved documents are also used for the new query for next step of retrieval. And next, the post-retrieval step. This is designed to enhance the accuracy and relevance of documents dynamically for real-time needs. This involves stepwise retrieval. For example, if 5 documents are needed, DIOR first selects the top 2 most relevant documents from the candidate area. Then it extracts newly emerging keywords or concepts from these 2 documents. And these new concepts are merged with the original keywords, and a new round of retrieval is conducted with the updated keyword set. This process iterates until the required number of documents are selected. And finally, to address the issue of long documents hindering LLM understanding, DIOR implements a sentence-level chunking module. It splits sentence into subclasses and evaluates combinations, and grouping them into blocks until the score for adding more subclasses decreases. And these segmented blocks are then integrated into the LLM prompt to generate the answer. Let's look on to the experiment. The experiment was conducted on 4 multi-hop benchmark data sets, which test various reasoning abilities for multi-hop to common sense reasoning. The domain of these datasets are all Wikipedia dataset. And they also use diverse retrieval strategies such as BM25, SGPT, and SBERT. And we can see DIOR consistently outperforms the baseline method for all datasets and all retrieval strategy. And when compared with other dynamic RAG methods, DIOR also stands out and achieving superior performance in here. And for ovulation study, they conduct the experiments without these four components in DIOR. And this clearly validates the efficacy of DIOR methods. So in conclusion, for contribution of DIOR is two components. So they address the limitation of effective timing for retrieval triggers and the retriever and retrieve content. They propose early detection to predict whether the LLM has the capability to answer a question prior to the generation. And for real-time detection, they detect in real time whether the output tokens from LLM are likely to be hallucinations. And for retriever and retrieve contents, they capture semantic relationship between contextual information for formulating the query. And they enhance retrieval accuracy with stepwise retriever. And they refine the retrieved documents before feed into LLM by sentence-wise chunking method. However, I think this paper has some limitations. There is no details about the method. It is unclear how to compute the score of subclasses combinations and how to formulate the query based on the top-ranked candidate keywords. And in this paper, only performance is reported for ovulation study of the method. They don't have any detailed explanation of their superior performance. And also, the classifiers such as early detection and real-time detection are trained and tested on Wikipedia domain. And their effectiveness in novel context beyond Wikipedia might be limited because the classifier operates only on IG scores or tokens during inference, as I understand. However, they train with richer context features such as like question, generated answer, gold answer, and IG and label. And I think it is just overfitting to hallucination-prone tokens within the training domain, rather than truly detecting the hallucination in novel context. But I'm not sure as I understand this paper. This is end of my presentation. Thank you for listening and feel free to ask questions.
Okay, thanks for presenting the paper, DIOR today. So any questions from student first?
I have a question.
Yes.
In the paper, the tokens were classified based on confidence to determine whether they were hallucinated or whether the model already know the answer to the query. But however, my question is that is confidence truly a reliable criterion for detecting hallucination?
Yeah, that was I also think about that, and I think that is the limitation of this paper. They only trained on wiki domain data sets, and I think they just trained the hallucination prone tokens to just so they construct the data sets for Wikipedia data set with these 5 components. However, for inference time, they only use this token and IG score, which means they just use the wiki domain characteristic. For example, when in Wikipedia domain, it is high probability to generate hallucination of this chemistry token. They just train this probability and just apply to test Wikipedia domain. So I don't think they really they truly detect the hallucination in novel context. Is it?
Yeah, so there was no supporting experiment about this fact, right?
Yeah, they just only report the performance of their method, and only they saying like our method have a high performance in this data set, and there's no details and explanation about this.
Okay, thank you.
Thank you for your question.
Yeah, so you mentioned that the paper only have the main experiment tables in the paper. So does it mean that there is no detailed analysis for their trained detection models in the paper?
Yeah, only this one. They just compare
Just observation. So one thing curious is that they did lots of things when in the time when they designed their two detection model. They say the early detection and the real-time detection. So they did lots of feature engineering, for example, introducing the new types of features extracted from the attention scores, the IG integrated gradient, I mean. So I really wonder if really the IG features contribute to improving the performance of detection model, but that kind of things was not covered in the paper, right?
Yeah, maybe they use IG score in early detection. So in here, without early detection, we can compare the performance improved. And the IG score is actually, it is from the another paper.
From the KDD paper they cited.
Yeah.
I see. So,
Here.
okay. So in terms of methodology for designing the two filters, there is no new insight they propose, just that they adopted existing off-the-shelf detection model or training pipeline to design it. And so the key novelty of this paper is the idea the idea of detecting the right timing to trigger the retriever while prior to generation. But this kind of thing, I also one thing unclear is that if we see the slide for the early detection model, the model received the generated text. Is it the answer generated from the model or other kind of things the model have to generate?
Can you?
So in the previous next slide, like the slide for early detection model explaining the input and output.
Yeah.
Yeah, not this page. Early detection, this page. In the data preparation step, if we see the data structures, they involved question and generated answer, right? So this detection can be triggered after completing generating the answers by the LLM. Is it right? But they mentioned that they do detections prior to generating something in the introduction. But
right.
the early detection and even also the real-time detection need generating something, right? So the early detection needs generating the full answer by putting it as the input to the early detection model, while the real-time detection ask the LLM to generate something, but token by token, and classify if the generate token at the current time is required to trigger some something more retrievers, right? So I think they, even though they mentioned that they do detection prior to asking generation to LLM, all of the filters or detection model indeed actually need generation by the LLM. So this is kind of mismatches with their saying and their methodological philosophy.
Yeah, right, right. It is also, and it is really strange. They use all of this data set for training, but for inference time, they use only the IG score.
Oh, they only use IG score without putting the generate answer from the model.
Yeah, as I
Mm,
understand, the
mm,
formulation of this retriever
mm, mm,
trigger
mm,
here, this is the early detection classifier with
mm.
RNN. They only use IG score in here.
That's why they use RLN. Because
Yeah.
in the time when we design the sequence of input, if we omit some kind of tokens in the middle, it's okay. The model can work, right?
Mhm.
But it's weird. I don't understand why the detection model can perform well, even though we only provide partial input to the detection model.
Because I think they train on Wikipedia data set and then test on Wikipedia, so they just train the pattern of the wiki domain, maybe.
Mm, I see. And then I also curious if there are some studies mm, for the latency and accuracy trade-off or the number of retrieval triggers
Ah,
in
they
processing of the query.
yeah, they have in appendix they compare the retriever trigger times. Um, is RC is
Oh,
oh, can you
yes.
see my screen?
I see. Yeah, I see.
RC is retriever count, and GC is generation count, and
Mm-hmm.
HC is hallucination count, and TC is token count, sentence
Mm-hmm.
count.
Mm-hmm.
So we can see here.
Efficiency of various retrieval and generation method. In second, I know not second. How can I read this table? What is the number? What does this number mean?
Actually, I didn't analyze this table, but
Mm-hmm.
I saw a case study of the DIOR here.
Mm-hmm.
So this is a baseline research, and this is a DIOR research. And DIOR has a low hallucination count, and also generation count is really low.
Mm-hmm.
However, the outcome is correct for DIOR and incorrect for
Mm-hmm.
baseline.
Then the base model is also one type of dynamic retrieval method
Yeah,
because they have more than one the SC and GC, right? They
yeah,
tried multiple generation and multiple retrieval.
yeah,
Okay. So they argue that their method is much more efficient than the default dynamic retriever RAG system.
yeah.
Okay. Hmm. And also, my last question is about the data they tested for their method. So, were the data actually does the data actually need multiple time of retrieval in terms of query complexity? The HAPA-QA, I think, it is quite easy in terms of query difficulty. So it doesn't trigger many time of retrievers to the RAG system. And
Uh,
IRC and strategy QA, I don't know what the data are. So could you explain a little bit on the data here and why the multi-turn retriever system maybe very helpful on those kind of data set? So IRC need integrating multiple document, generating the question, and strategy QA designed to assess common sense reasoning. That involve implicit strategy. I see. So inherently, all of the benchmark data they utilize need integrating multiple document to make the answer, but not possible to answer even only with one document searched.
Yeah, right.
Okay. Yeah. Okay. Great. So yeah, thank you. That's all from my side. And other question from other people? Okay. So no question from other students and other people. So let's try to wrap up here. So thanks again for preparing your presentation today, Minjeong Ban. And next week, the presenter is Donghyun Shin from GIST, and he will talk about the paper title from RAG, a similar topic with what we reviewed today. So from RAG to memory, non-parametric continual learning for large language model. Yeah. Okay. Thank you. Yeah. Have a great day.
Thank you.
Bye.